So, what is electrochemistry? Electrochemistry is the study of the relationships between electricity and chemical reactions. This includes the study of both spontaneous and non-spontaneous processes. So you see how that goes back to us talking about thermodynamics 2 weeks ago, right? It connects back to that. And when we're talking about electricity, what we're really talking about is the flow of electrons, right, in reactions. Okay, the flow of electrons in reactions. So if we take a look at give subtitles. Why do I need subtitles? I don't need subtitles. That's weird. Okay, so if we take a look at what the gist of electrochemistry is, which what we're talking about here is basically oxidations and reductions, right? Because that's the loss and the gain of electrons. Okay. So first thing we got to figure out is how do we do like oxidation numbers? And this is just it's not even a figure out. You've already done oxidation numbers back in Gen Chem 1. So it's not really a figure out, but it's just a little reminder, right? Remember that elements, like elements on the periodic table, they all have oxidation numbers of 0, right? Most of the time, though, they're not happy with that because they want to, pull electrons from somewhere else or lose electrons to get to the octet of 8, right? To get a full shell of 8, an octet, and then their oxidation number will change. But as is, though, on the periodic table, elements have an oxidation number 0, right? Monatomic ions have a charge. So, example here, remember that fluorine has a charge of -1, right? And then oxygen has a charge of -2, right? Unless it's two oxygens together, like peroxide, then it's got a charge of -1. And then hydrogen here, which is basically a proton, has a charge of +1, unless that hydrogen has an electron attached to it, and then it becomes a hydride, and then it's got a charge of -1. And we actually talked about hydrides a lot last couple weeks ago, because it's a hydride plus a proton that gets added to NADH or NAD to become NADH and FAD to become FADH2 in glycolysis and the TCA cycle, right? So we've heard of hydrides before. So the sum of the oxidation numbers overall in a compound will then equal 0 in a compound, right? So the charges will all equal out to 0. But when you have those ions separate, each one can have its own oxidation number. Okay. So let's just quickly look at this here, right? To keep track of what loses electrons and what gains them, we assign them oxidation numbers, like I said before. And if the oxidation number increases for an element, then it's oxidized, right? If the oxidation number decreases for an element, then it's reduced. So basically that means that if the oxidation number goes down, the element gained electrons. If the oxidation number goes up, it lost electrons. Okay? Does that make sense? It's a big thing right there. Okay, so we're going to use this example here. I think this is the example on the next slide. I hope it is anyway. But here we have zinc metal, right? And we'll add to it some hydrochloric acid, and then it becomes zinc chloride and hydrogen gas, right? Hydrogen gas. So this actually is a redox reaction, right? This is a redox reaction. And you can see here, for example, zinc here actually had 2 electrons, had a single electron, right? But then it lost that electron and it became zinc chloride, right? So this is definitely a redox reaction. So let's actually look at it very closely in the example ahead, except that we have our first question. So the vast majority of you got this correct. The answer is in fact D. I'm gonna have to figure out who that was. I got it wrong. It means they weren't paying attention. I'll look that up in a minute. Okay, so let's keep going. I don't want to waste time on this. I'm just playing with you guys. Anyway, so let's talk about this again. We've talked about this so many times, right? When a species is oxidized, it loses electrons. So as I was saying in that reaction we saw in that picture, zinc loses 2 electrons, becoming the zinc chloride, right? I'm sorry, becoming the zinc 2 ion, which becomes zinc chloride in the reaction, right? Which I'm sorry, I think I may have said zinc 1 previously. It's actually zinc 2. And then the species that was reduced, right, gains electrons, and the thing that got gains electrons is the protons. It got an extra electron, right, forming H2 gas, right? So the oxidizing agent here, right, an oxidizing agent here, which is proton, causes something else to be oxidized, whereas the reducing agent causes something else to be reduced, right? So we have the oxidized species, which is the thing that lost the electrons. We have the reduced species, which is the thing that gained the electrons. But then we have the oxidizing agent, which did the oxidizing, and then we have the reducing agent that did the reducing. Make sense? So basically, the agents are the opposite of what? The oxidize and reduce. Okay. So like I was saying before, we're sticking with this as our example in our redox reaction, our oxidation reduction reaction, right? We begin here with zinc solid, right? And zinc solid here is introduced to protons from the hydrochloric acid, right? And so zinc here has an oxidation number of 0, right? Individually, each proton has an oxidation number of 1, okay? And then what happens is that the zinc loses 2 electrons and becomes 2, zinc 2 plus, right? And then the hydrogens gain the electrons and they become hydrogen gas. And so now the oxidation number of zinc is 2 plus or plus 2. And then the hydrogen gas has an oxidation number of 0, right? And you see it in the equation as zinc chloride, right? But here, we're just talking about the species that are losing electrons or getting electrons, right? The zinc lost electrons and became plus 2, right? And the hydrogen gained electrons and became hydrogen gas. Okay, so back in Gen Chem 1, we did this thing called balancing chemical equations. If you recall that, you all recall balancing chemical equations, right? Well, now we're going to have to do what we call balancing redox equations, oxidation reduction equations, and they're a little bit more complicated, just a tiny bit, right? And so when we want to do balancing of an oxidation reduction reaction, we have to use what we call half reactions. Okay, what we have to use is what we call half reactions, right? So in an oxidation reduction, they're written balanced separately, right? We will use them to balance a redox reaction. So for example, when tin 2 and iron 3 react, right? We get here the 1/2 reaction is with tin here losing electrons, right? So tin 2 becomes tin 4 and then plus 2 electrons. And in the reduction part, iron 3, right, gains those 2 electrons and becomes iron 2, right? So in redox reactions, we have to split the reaction in half, right? The reduction side and the oxidation side, right? And we have to balance them separately. And you've seen here already, part of balancing it is balancing it by putting coefficients, right? Which you already know about, right? Which you've done before. But then you also have to balance out the charges by adding electrons, okay? So, let's see here, right? Okay, so this is just a synopsis of how we balance half equations, okay? How we balance half equations or balance redox equations using the half reaction method. First thing you do is you take the reaction, the redox reaction, you make it 2 half reactions, an oxidation reaction and a reduction reaction, okay? And then you start out by balancing all the atoms with O's and H's, right? With O's and H's. Sorry, let me say that again. You balance out all the atoms other than the ones that are O's and H's, okay? So if you have anything else in there like zinc, chloride, anything that's not an O and not an H, you balance those first. And then when you get to the O's and H's, you got to balance those. You balance those out by balancing them using waters and protons. Okay? Waters and protons. After you do that, you add electrons to balance the charge. And then you multiply by the common factor of the electrons so that you have the same number of electrons on both sides of the equation, right? They end up canceling each other out. And then you add the half reactions to each other. And then you have the full reaction. Okay? So then you simplify so this is if you have a base, right? If you have a base, you simplify the reaction by dividing by the common factor and canceling out any waters that came from adding protons to hydroxides. So the thing that's confusing about this is that when you do a redox reaction that is in acidic conditions, all you really have to use is waters and protons and electrons, okay? But then if you're doing it in a basic solution, you've got to use all those 3 things plus hydroxides, right? And those hydroxides turn the protons into waters, and those waters can get canceled out after you do the adding of the thing, right? And I know the steps are kind of difficult right now, but when you see it happening, it's actually really easy. So last thing you do is you check, and what happens is that when you're completely done, Both sides should have the same number of atoms, like you should always do in a balanced chemical equation. But the more important thing is that the both sides will have the same number of charges, right? If one side has a +6 charge at the end of it, the other side will have a +6 charge at the end of it, right? If one side has all the same number of oxygens, the other side will have all the same number of oxygens. If one side has all the same number of protons, same thing on the other side, right? So our next question is this. Which of the following is not a step in balancing redox reactions? Make two half reactions, right? Balance atoms other than O and H, and then balance O and H using waters and protons, right? You subtract electrons to balance the charges, or you multiply the common factor to make all the electrons half reactions equal. All right, let's see how people are answering this question. Okay, everybody's in, and I am so very proud. It means everybody's paying attention because everybody got that one right. There is definitely no subtracting. Whoops. There is definitely no subtracting involved in the balancing of redox reactions, right? So good job, everybody got that one correct. The answer is indeed C. Good job. Okay. Okay, so let's use this reaction now as our example reaction for doing redox balancing, right? So this is a reaction between permanganate, the ion, right? The MnO4 minus is permanganate, I'm pretty sure. And then the other ion here is oxalate. I'm pretty sure it's oxalate, right? So usually in this kind of reaction, remember when you did a acid-base titration, right? Well, this is what we call a redox titration. And the species or the chemicals we use in redox titration are generally potassium permanganate, which is the purple color, and the oxalic acid, which is the clear color, right? And you do a titration the same exact way as you would do an acid-base titration. But we still need to balance out these equations, okay? So that's why we know then that this is actually the permanganate ion and this is the oxalate ion, right? And so this is the redox reaction we have. Permanganate, which is MnO4 minus in aqueous solution, plus oxalate minus 2, right? 2 minus in aqueous solution, becomes manganese, right? 2, and then carbon dioxide in the solution, right? Carbon dioxide in the solution, okay? So first thing to do, right? First thing to do is assign the oxidation numbers, okay? We see that manganese here began with a +7, right? And then it became a +2, right? And then carbon, so that means that manganese got reduced, right? When you go from +7 and you go down, that means you got electrons. So that's a reduction. So manganese got reduced. And then carbon dioxide, right, got oxidized, right? It went from a +3 to a +4, which is interesting because you already know from previous lectures that when you add on oxygens, that's automatically an oxidation anyway, right? That's why we call it oxidation, right? And so in this reaction then, manganese is the one that's getting reduced, carbon is the one that's getting oxidized, right? And those are the oxidation numbers, okay? So let's go ahead and split them up into the half reactions, right? So here we have the oxidation half reaction, oxalate becomes carbon dioxide, and so the first step was to do what? Balance everything but the what? Oxygens and hydrogens, right? So we have a single carbon on the right side. We have 2 carbons on the left side. How do we balance this? All we have to do here is to put a number 2 as a coefficient in front of carbon dioxide. And now we have 2 carbon dioxides on the right side. And we also have 4 oxygens on the right side, which is the same as it is on the left side, right? Good stuff. Good stuff. See, this part's the easy part, right? So next, right? The problem now, though, is that once you've balanced it, right? Once you've balanced it, you still have a -2 charge over here, but you have a 0 charge over here, right? So the way you balance this charge-wise, right, is by adding 2 extra electrons, right? So now these 2 right here, -2 right there, is balanced by these 2 electrons over here, okay? And you might have to add electrons on either side. It just depends. If you're doing an oxidation reaction or a reduction half reaction, right? But on this one here, carbon dioxide is definitely getting oxidized, right? And so since it's getting oxidized, you can see that it becomes 2 electrons separated from the carbon dioxide. And that's why you know this is an oxidation half. And so remember, -2 on this side gets balanced out by 2 electrons on that side. Okay? So we're done balancing the oxidation side of the half reaction. So now let's do the reduction side of the half reaction. We have manganese here, right? Or permanganate rather. And permanganate became manganese 2, okay? And so how do we balance out oxygens? Well, we balance out oxygens by using water. So you need to have 4 oxygens here, right? You need to have 4 oxygens to balance out the number of oxygens that are on the left side. How do we do that? We add 4 waters because that gives us 4 oxygens. Does that make sense? Right? We have 4 waters because that gives us 4 oxygens. Okay? Then we've got to balance out all the hydrogens that we put out here on the left side, on the right side, right? All these hydrogens from the water here. So there's a total of 8 there. How do we do that? We balance that out by adding 8 protons to the left side, right? So now there's 8 protons or 8 hydrogens, and there's 8 hydrogens right there, right? And then there's also 4 oxygens, right? And then we still have 1 manganese. So all the atoms are now balanced, right? But what's still not balanced yet? Exactly, the charges are not balanced yet. Okay, so now we got to balance the charges. To balance out the charges, right? To balance out the charges, we have 8 positive charges over here, right? Plus a minus charge here, so that actually gives us a total of plus 7 on this side. And over here on this side, we only have plus 2. So how do we get the plus 7 down to plus 2? We add what? 5 electrons, right? Because 5 minus charges brings us from a plus 7 to what? A plus 2. Make sense? Right? So now our equation looks like 5 electrons plus 8 protons plus permanganate minus 1 makes manganese 2 plus 4 waters. So notice that since this is the reduction one, right, the electrons are being added to which side? The left side, right? But on the oxidation half reaction, where were the electrons added to? The right side, okay? Now we combine them all together, the 2 halves all together, right? We have this guy here, right? And we have this guy here, right? And the thing that we have to do now is to make it so that we have the same number of electrons on both sides. Because on this side, we only have 2 electrons, and then on this side, we have 5 electrons, right? So what's the most common multiple for 5 and 2? 10, exactly. So you multiply everything by 10. You multiply everything up here by 5 to get that to 10 electrons. And then you multiply everything here by 2 to get that to 10 electrons, right? And so that gives us the following. Okay? So now we got 5 oxalates makes 10 carbon dioxides and 10 electrons. And then 10 electrons plus 16 protons plus 2 permanganates make 2 manganese 2s plus 8 waters, right? Then we add both of them to each other. We add both of those reactions to each other, which is as easy as just putting everything that's on the left side together, and everything that's on the right side together, right? So now we get this equation here, right? Where it's 10 electrons from the manganese side, right? 16 protons from the manganese side, permanganate side, 2 permanganates, right? And then 5 oxalates on the left side. And then on the right side, we have the 2 manganeses, plus 2s, plus the 8 waters, plus the 10 carbon dioxides and 10 electrons. Notice that the 10 electrons are on both sides now, so you have balanced number of electrons on both sides, right? Or the same number of electrons on both sides, okay? Excuse me. So after we have this entire equation, right? After we have all these equations, what we can do is, since we have not discovered, but we have figured out the number of electrons being transferred, we can actually cancel out both of those electrons, right? Because we know that those electrons are there. We can just cancel them out. So what happens is that at the end of this process, if you don't have the same number of electrons on both sides, you've done something wrong, right? That's how you know you've done something wrong, okay? So you can get rid of the electrons on the side, you can get rid of the electrons on that side, right? Just subtract them out on both sides. This is the only time that you actually subtract anything. You subtract out the electrons, right? After you get the same on both sides. And then that leaves us with our final equation, which is 16 protons plus 2 permanganates plus 5 oxalates gives us 2 manganese 2s, 8 waters, and 10 carbon dioxides, and a partridge in a pear tree, right? So at this point, you can go through and add up all the charges and add up all the different individual atoms, and it should be the same on both sides, right? So yes, redox reactions, when you balance them, are much more complicated than doing a regular chemical equation, right? But as long as you follow the steps, it should be pretty simple, okay? Right? Start out by, let's go over real quick one more time here. Oopsies. Start out by splitting them up into their half reactions, right? Remember, you split them up into their half reactions. So the manganese and the permanganate to the manganese, right, go together in the reduction reaction. The oxalate and the carbon dioxide to go together in the oxidation reaction, right? First thing you do is you just balance everything normally without balancing any of the oxygens or the proton or the hydrogens, right? You do the coefficients like a normal chemical equation, right? Then you balance out the charges with electrons, -2 over here, so you need a -2 on that side, right? Same thing with this here. This was already balanced with all the other atoms except for oxygen, so the only thing you had to do here is add in the 4 waters to make oxygens. But the problem with adding in 4 waters is you end up with 8 protons here, so you have to add 8 protons over here to balance that out, right? Now you have the same number of atoms on each side, but you still don't have the same number of charges on both sides, right? So then you've got to go and add in 5 electrons on this side to balance out all the charges. Excuse me. And then you go through and combine the half reactions, and then combine the half reactions. But the first step in combining the half reaction is to make sure you have the same number of electrons on both sides. So in this case, it's going to be 10 for the lowest common multiple, right? Multiply that by 5, multiply that by 2, and you get 10 electrons, all the numbers, right? And then you get the this equation here, right? You get that equation there when you put it all together. And then after you put it all together, all you do is you get rid of all the electrons, and then you get the completed equation. Any questions? Right? Okay, so here is your next question. What is the first step in balancing the reaction between permanganate and oxalate? Balance the oxalate to carbon dioxide oxidation half reaction. Balance the permanganate to the reduction half of the manganese reaction. Determine the oxidations of each species. Determine the species that was oxidized and reduced, or balance the charges. Beautiful. Okay, so this is the distribution right here. Kind of a mixed bag, right? But I will say right now, though, that the answer is indeed C. The answer is C, right? Because before you can even balance out the carbon dioxide side, the oxalate on carbon dioxide side, and the permanganate and the manganese side, you have to figure out what species is actually getting oxidized and what species is actually getting reduced, right? Like you don't have to actually figure out what the oxidation numbers are of each of the species, but you have to be able to know which one's actually getting oxidized and which one's getting reduced, so you can actually make the correct what? Half reactions, right? Because if you don't make the correct half reactions, then you won't be able to balance each half reaction correctly, right? So I definitely would go through and if at the very least, figure out which species is getting oxidized and which one is getting reduced first, and then start balancing the half reactions, right? You don't have to actually figure out the oxidation numbers yet, but I would definitely figure out at least which one's which because you won't know which one's the half reaction for the redox side, the reduction side, and which one's a half reaction for the oxidation side, okay? So, like I was saying before, right, when you're doing it in a basic solution, it's a little different. you do all the same things, right? You do all the same things as you do in an acidic solution, right? Uh, Except that once you get done balancing everything out, right? Once you're finished balancing and pretending it's an acidic solution, the next thing you've got to do though is you've got to add hydroxides to the water to the equation, right? So that you can neutralize the protons, right? So that you can neutralize the protons. Okay, you got to do that first. Okay, and so when you do that, your equation will actually make water, right? It'll turn a lot of the protons, or all of the protons, into waters, right? And when you have waters on both sides, right, you can actually cancel out the waters. Okay, you can cancel out the waters. Okay, so so this is another situation when we subtract water, but really you just get rid of the waters because if you have the same number of waters on one side, and you have like the same number of waters on the other side plus one, then you can cancel all that out and just leave that one water left over. Okay, so and the reason why we have to do this is because when you're in a basic solution, the hydroxide is there, right? And what is it going to do? It's going to go in and take up all those protons, right, and turn it into water. So you can't just leave it as protons like we did in the acidic reaction. Okay. All right. So that takes us to talking about voltaic cells. Okay, voltaic cells, right? In a spontaneous reaction, right, electrons are transferred and energy is released, right? That energy can do work if the electrons flow through an external device, and this is called a voltaic cell, right? This is called a voltaic cell. This is very similar to like when people stick like electrodes into like a lemon or a potato, right? And then they can charge their phones with it, right? It's actually pretty neat. I should have done that today. Maybe that would have gotten you more interested in what was happening. So, but I didn't think about that, right? So here in this particular voltaic cell, right, we have two electrodes. We have the zinc electrode and we have a copper electrode, right? And then we have this cool little beaker here that has tubes in between, right? It's got tubes in between, and there's a porous disc in these tubes, right? And what happens is that the blue solution, you always know the blue solution is blue. Blue solution is blue, of course it is. Copper, the blue solution is copper, and the zinc sulfate solution is the clear one, right? And then a redox reaction will occur between the zinc and the copper. And when that happens, you can actually get a current. You can get a current, right? You can get a current flowing through. It's kind of neat. Okay. Anyway, so let's talk about voltaic cells in detail now with our zinc sulfate solution and our copper sulfate solution here, right? So this is what these are. Okay, just to be clear, you need to know your vocabulary words. Okay, you need to know your vocabulary words. And so in a voltaic cell, the oxidation, right, occurs at the anode, and then the reduction occurs at the cathode, right? So when electrons flow, charges aren't balanced. So a salt bridge, usually a U-shaped tube containing salt and vinegar solution, is used to keep the balances charged, right? And so here we have, oh, here's the salt bridge right here. This is a salt bridge, okay? And so here's your zinc, right? So your zinc here is the cathode, I'm sorry, the anode, right? Your zinc here is the anode. So the zinc is sitting in the zinc solution, right? The zinc is sitting in the zinc solution over here, right? And oh, that's so funny. Um, this side we have sodium nitrate instead of. I was hoping it would be the same thing as what we said before. I wonder why they changed it. I was hoping it would be the example of this, but that's okay. So, same principles, same principles. Anyway, so here we have the zinc side, right? And you can see that electrons, right, are moving away from the zinc, right? They're moving away from the zinc, okay? And so as electrons move away from the zinc, we call this the anode side because that's the side that's getting oxidized, right? And as electrons flow from the zinc metal in the wire to the voltmeter or the multimeter, right? We make zinc 2 ions in solution, right? We make zinc 2 ions in solution, okay? So now we have down here, right, the solution of like zinc nitrate and we're making more and more zinc too, okay? As the zinc is getting oxidized, those electrons have to go somewhere, and those electrons are going to flow through the wire into the multimeter and give you 7.76 volts, right? So you can actually do this in lab, which we're not going to do this in lab, but you can actually do this in the lab and see like two solutions actually making a voltage, which is kind of cool. I mean, you can't really do much with 0.76 volts, but you know, it's kind of cool to see. So we bring it over here, right? And this is the cathode side because here we're getting the electrons, right? Here we're getting the electrons, and so um, uh, the the electrons here are getting added to the protons, and you're making hydrogen gas, right? And you're making hydrogen gas on this side, right? And so it's pretty neat that you can actually do this, right? Okay. All right. So a little bit more about voltaic cells, right? In a cell, the electrons leave the anode and flow through the wire to the cathode, which I just said that, right? So here's the anode right here, right? And the electrons flow through the wire to the voltmeter right here and over into the cathode, right? So electrons flow from the anode to the cathode, which I said that in the previous slide already, right? Cations are formed at the anode compartment. So this is over here, right? Over here, the cations over here are being formed. So in the previous example, those cations were the zinc 2s, right? The zinc 2 pluses that were being made when the zinc was losing its electrons, right? The zinc electron was losing its electrons, right? And then as electrons reach the cathode, the cations in solution are attracted now uh, to the negative cathode, right? So the cations will actually pass through and go into the other side, right? And then the cations gain electrons and are deposited as metal on the cathode, right? So in I guess in the zinc one, right? The zinc uh, the zinc the zinc ions, the zinc 2 pluses are passing through here. They'll regain their electrons, right? And then deposit themselves on this cathode, right? So eventually the anode is just going to run out of metal if you let it run forever. I don't know if you can let it run forever, but that would be interesting, right? If you put a very small piece of zinc there and see how long it takes for it to completely uh, get oxidized and become, over here, that's pretty neat. So here's your next question, right? Which of the following is not true about voltaic cells? Electrons leave the anode and flow through a wire to the cathode. Sounds reasonable. Anions are formed in the anode compartment. As electrons reach the cathode, cations in the solution are attracted to the now negative cathode. And then cations gain electrons and are deposited on the metal cathode. The most of you got that one right. Good job. You paid attention to my thing, right? To my lecture. Most of you did, anyway. Most of you paid attention and got that one right. In fact, anions are not formed in the anode compartment, right? What's actually formed in the anion compartment? I mean, what's actually formed in the anode compartment? Cations, exactly. See, electrochemistry is so easy compared to everything else, right? I mean, I'm running out of excitement for it, but it's so easy, right? So there's this thing called the electromotive force, also known as EMF, right? EMF, not to be confused with the stuff that they use to detect like ghosts. What's that called? EMP? No, not EMP. EMP is electromagnetic pulse. EMV? Maybe it is called EMF. Electromagnetic frequency? Yes, so I'm pretty sure it is EMF, but that EMF is actually electromagnetic frequency. This EMF is electromagnetic, no, electromotive force. There we go, electromotive force. So what is electromotive force? What? Thank you. Anyway, so water, right? Water flows spontaneously in one direction in a waterfall. Okay. So comparably, what do electrons do? They also flow in one direction, right? Spontaneously in the redox reactions from a high to low potential energy, right? From a high to low potential energy. So in your biology classes, have you used anything for like gel electrophoresis before? Gel electrophoresis? Yes. You add in DNA to the gel and then you watch the DNA flow. It's the same thing. That's electromotive force, right? The thing that's moving the DNA on the gel is the fact that electrons are flowing, right? But then DNA also has a very negative charge because the backbone is made of a phosphodiester backbone, which is very negative, right? So they all flow together, right, from the negative side to the positive side. And that's how DNA gels work, right? Protein gels work the exact same way. And that's what we're talking about right here. This is called the electromotive force, right? So notice, again, we have here an anode, right, which is high potential energy. The electrons flow, light a bulb, and then into the cathode, right? So from high potential energy to low potential energy, right? So if I have a true/false question for you that says that electromotive force says that the electrons will flow from a low potential energy to a high potential energy, is that true or false? I said low to high, but all right, whatever. Oh, your brain was focused on the picture, not what I was saying. Yes, but if I had a true or false question and I said it was going from low to high, that would be what? That would be false. Exactly. Right. So anyway, all that is to say this, right? Uh, the potential difference between the anode and the cathode is called the electromotive force, right? The electromotive force. It also has the thing called the cell potential, right? It's also called the cell potential, and it's designated with this little thing here called the E cell, right? The E cell, right? And it's measured in volts. 1 volt is 1 joule per coulomb, right? So when you see 1 volt on your, like for example, a double A battery has 1.5 volts, right? 1.5 volts, right? That's the same thing as saying 1.5 joules per coulomb, right? And that's the electromotive force of the battery. Make sense? Right? Good stuff. See, you're learning so much today. So much. So, which of the following is true of EMF? Right? The potential difference between the anode and the cathode in a what the heck? I forgot to put something there. Maybe that's the one that's I didn't finish that answer. It is also called the cell potential. It's measured in volts, right? That was a mistake. I wasn't trying to trick you there. I don't know what happened to the end of that answer, right? The answer here, since I messed this one up, should be all true. So I don't know what happened there. So sorry about that. Yeah, it should be all true. I guess I was when I was copying and pasting, it got cut off, right? No, it's D. It's supposed to be D. It's supposed to say the potential difference between the anode and the cathode in a cell is known as the EMF. So it should be D. So since I screwed that one, I screwed the pooch on that one. We'll keep going. Keep going. So now that you know about potentials, there's this thing that we call standard reduction potentials. And the standard reduction potentials are the reductions of many electrodes that have been measured and tabulated, right? And the values are compared to the reduction of hydrogen as a standard. And these are at standard conditions. And remember, I told you about knowing what the standard conditions are a couple weeks ago, right? The standard conditions are at 1 molar, 1 atm, and 25 degrees Celsius, or the Kelvin equivalent, right? Of 25 degrees Celsius, which is what? What? You just making up numbers?
273 Kelvin.
Yes. Plus 25. 289. Oh, wait, 290, 298. Sorry. I got dyslexic there. 298. There we go. Or what is that called? Is it called dyslexic or is it called dyscalculic? Yeah. Yeah. It's okay, time out. It's 298. It should be 273 plus 25. Plus 25, which is 298. Where does the 0.5 come from? What? Where are you getting the 0.5 from? You must be. No, well, to change anything from Kelvin to Celsius, you just add the 273. So if you were at 25 Celsius, right, then you just add that to 273. Does does that make sense? Where are you getting the 0.5 from? That's maybe that's true. But I only say that because a lot of times in the problems I'll give you, it will be in Kelvin. Okay? Okay, it will be in Kelvin. So, okay, I apologize for this here. For some reason, when I opened up this file, all my things got messed up. So these little AE looking things, right? They look like American Eagle logos, like the clothing company. Those all should be arrows. Arrows, arrows, arrow, arrow. All those should be arrows. Okay, all those should be arrows. I don't know why those arrows became A&E logos, right? Or it could be A&E the channel, right, where you watch Hoarders and what else was there on A&E? Storage Wars. Pawn shop? You mean Pawn Stars? I thought that was on History Channel. Is that on History Channel? I don't know. Anyway, so the point is here, know that all these standard reduction potentials are based on hydrogen being the base, right? And these numbers here, right, are the standard reduction potentials for example, fluorine getting reduced, becoming two fluorides, right? Or permanganate right here, right? And becoming manganese, right? Getting reduced, right? So obviously it's a reduction potential. So all these things are getting reduced. You can see electrons being added to them and then becoming, for example, silver 1 here gets an electron added and becomes silver solid, right? And that's a reduction potential of 0.8. So you don't have to memorize these numbers, but I do want you to notice a trend in the numbers, and we'll talk about that in a second, right? Again, I don't know why I did this, but again, all those A&E logos should be arrows. My apologies there. But I just want you to see this here based on hydrogen, right? Or two hydrogens or two protons get two electrons, they become H2, right? That's 0, right? So everything else is based on 0 reduction potential, which is hydrogen, okay? And this is just a continuation of that chart, which you can look at it more later, right? So, all right. So the standard hydrogen electrode, okay, which we saw that a second ago when we were talking about the zinc thing, the zinc voltaic cell, right? So the reference here is called the standard hydrogen electrode, which is also known as She. She. That reminds me of that drug that's on TV. What is it? Something HER2 negative or something? You know what I'm talking about? Something HER2 negative, whatever. Anyway, by definition, as a standard, the reduction potential of hydrogen is 0, right? And of course, that's at 1 molar, at 1 molar and at 1 ATM, right? And so here you can see the She, or the standard hydrogen electrode, right here, right? And we've got platinum here, right? And some protons here, right? And then platinum is getting getting oxidized, and hydrogen is the protons are becoming H2 in this reduction, right? On the other side here, though, we have H2 molecules reducing the metal, right? And then they're getting oxidized, becoming protons, right? So the She cathode, She as a cathode, protons are being reduced to hydrogen gas, but a She as an anode, right? Hydrogen gas is being oxidized to a proton, okay? And so that's what all the standard reduction potentials are based on, okay? And so that brings us to this last slide I want to talk about today, and then we'll have one question, and that'd be it for today, okay? You can actually, don't leave yet, we have one question. Are you leaving or are you stretching? Oh, okay. I understand, my back hurts too. I went all out with my Christmas decorations this year, and my back is killing me. Anyway, so you can calculate standard reduction potentials, right, by doing the reduction, the reduction potential for the reduced of the cathode minus the reduction potential for the anode, right? And that will give you the entire reduction potential, the standard reduction potential for the entire cell, okay? So that's an equation you'll need later on in life, which we will talk more about in more detail on Wednesday. So the last thing for today is this question here, right? Which of the following is not true about standard reduction potentials, okay? The values are compared to the reduction of helium as a standard. Standard conditions are 1 molar at 1 atm, 25 degrees Celsius. By definition, as one standard, as the standard, the reduction potential for hydrogen is 0 volts. Or you can calculate the potential, the cell potential at standard conditions through the equation of the E cell equals the E reduced of the cathode minus the E reduced of the anode. And this is our last thing for today. Huh? Still waiting for 5 people. Four people. I guess I'm not waiting for 8 people anymore. Now I'm waiting for 7 people. So 2 more people. 7. Oh, okay. Everybody's there. Everybody's there. Okay. The distribution here is everybody except for one person got that one right. Yes, exactly. Good job. Good job. People paying attention. The answer here is, in fact, it should be hydrogen is used as the standard, right? This is the correct equation, so it's not D. A is correct. Good job. So what you can do then is you can get the reduction potential of the cathode and the reduction potential of the anode, and then that will actually give you the cell potential, right? And the cell potential is it's very similar to like if you have a battery and it's like a 9-volt battery, right? That's the cell potential of a 9-volt battery, for example. Or if you have a car battery, right? The car battery is 12 volts, right? 12 volts, right? So that's the cell potential right there. But you can also use that because it is the same thing as that cell voltage potential that's in batteries is the same thing that we do in all chemical reactions because what electrochemical reactions, because what is a battery but a chemical reaction, right? You hear things like lithium ion batteries. So what do you think is the ion in lithium ion batteries? Lithium, right? Or car batteries are usually sulfuric acid, right? Alkaline batteries, everybody knows those. So, and then the other thing is you can get the cell potential by getting the standard reduction potentials of the cathode and the anode, and oftentimes you can find that in the chart that I was telling you about before, right? And if you weren't here on Monday, just to be clear, somehow when I made my PowerPoint, all the arrows here got turned into A&E logos, American Eagle logos, right? So all those A&Es right there should be arrows, okay? So knowing what a cell potential is, right? Knowing what a cell potential is, right? Just know that there's a difference between having the cell potential, right? Which is the difference between the two standard reduction potentials, right? The standard reduction potentials are the reduction potentials, like the tendency for one of the electrodes to lose an electron, right? Whereas the cell potential is actually the difference between the reduction potential of the cathode and the anode. Okay, so expect questions in the multiple choice section about the relationship between these things here. Okay, so we already answered that question. So let's take it to cell potentials now, right? So if you have an anode of the cell, right, and the anode's reduction potential is negative 0.76 volts, right, and the cathode is its reduction potential is 0.37 volts, right? Again, these numbers come from a chart. They've already been determined for you, and they come from a chart, right? And then you can figure out what the entire cell potential is, right? Think of it as a battery, right? By plugging it into that equation I just showed you a second ago, which is right here, the difference between the anode and the cathode reduction potentials, right? And so all you have to do is 0.34 volts, and then minus, and then you do the you do minus, and then you do the negative 0.76 from the cathode, and that gives you a total of 1.1 volts, right? 1.1 volts. That's kind of like a double A battery. Well, I think a double A battery has 1.5 volts, right? So this is just a picture here describing what a cell potential is, right? So we have a zinc copper solution with zinc and copper in there as the electrodes, right? The zinc is the anode, right? Yeah. Oh, that's weird. I know, I just saw that. Ah, killing me. Okay, um that's really weird. I wonder why. This right here is wrong, right? The numbers are correct. This is a typo. The anode should be over here, and the cathode should be over here. The numbers are correct. It was just a typo. Okay. Yeah. It should be cathode minus anode, right? Okay. Yeah. So I don't know why that happened. That's really weird. That's super weird. I don't know why that happened. Anyway, too fast typing, I guess. Anyway, so back to what I was saying before. I apologize for that. Make sure in your notes you fix that, right? Because I don't want you to. Well, on your exam, I'll give you the equation on the exam. So I guess you don't have to worry about that, right? So, but on the exam, I'll give you the equation. But just for your references, and when I guess while you're doing practice problems, right? Make sure you're subtracting the anode from the cathode, not the cathode from the anode. That's really weird. Okay. All right. So here's an example of what the cell potential is about, right? An image showing you what the cell potential is about, right? We have here a salt bridge connecting a zinc solution with a copper solution. The anode is the zinc, right? And then the electrons flow away from the zinc, right? So that's why it's the anode. And then they go towards the cathode. The electrons are flowing towards the cathode right here, and the cathode here is copper, right? And so we were talking about this before, right? On Monday, where the zinc metal, right, actually loses electrons. It becomes zinc 2, right, as the electrons leave, giving you, if you have a voltmeter there, you can actually test and see what the voltage is of the cell is here, and it gives you 1.1 volts, which is super close to the actual experimental, right? Like if you did the experiment and you read the number, it's actually very close, right? And then they go towards the cathode. The copper here, right, is actually receiving those electrons. So interestingly enough, at the very microscopic level, and I talked about this a little bit on Monday, right? If you leave the zinc here for too long, eventually you'll run out of, it might take a gazillion years, right? But eventually you'll run out of zinc because all the zinc becomes zinc 2, right? But the cool thing about it though is that as those electrons flow over the circuit right here over to the copper electrode, the copper 2s in this copper sulfate solution actually become copper. So as the zinc goes down, right, like gets less, you lose the zinc metal because it becomes zinc ions. You actually turn the copper ions into what? Copper metal. So you get more copper, right? Isn't that cool? So eventually, if you left it there for a couple, maybe a few years, I don't know why you would do that, but if you left it for a couple years, uh, you'd run out of zinc, right? Because it all go into solution, and you have a really big piece of copper, right? The copper would increase, right? So that kind of relationship is something that you need to know, okay, for the exam, okay? Because I will ask you questions like, if I have this and this solution and this and that solution, this is the anode and this is the cathode, right? What will happen to what will happen to one of them over time, and what will happen to the other over time? Does that make sense? Okay, so I really need you to, those are the kind of questions I might ask you on the multiple choice part of the test, right? So again, here's the standard reduction potential right here for the zinc, right, at negative 0.76. Standard reduction potential here for the copper here at 0.34, right? You plug it into the equation and you get 1.1 volts, right? And just so we're clear, where that number comes from. Where do we get the negative 0.76 and where do we get the 0.34, right? Which you saw this chart already before in the lecture, right? But let's go back anyway to make sure that everybody's clear on this. We'll go to the chart that's missing arrows and has A&E logos on it, right? We have here zinc, right? Negative 0.76. Copper here, right? 0.34, right? So 0.76, remember that was actually in a negative parenthesis, so that turns into positive. So 0.76 plus 0.34 is what? 1.1 volts, right? Make sense? That's where those numbers come from, okay? So make sure that you know that we're not just making up these numbers. They come from somewhere, right? And you can use these numbers in the calculations that are going to come up, okay? All right, so, okay, so oxidizing and reducing reagents, we talked about this before, right? When you have an oxidizing agent or reducing agent, it's just the opposite of what's getting oxidized and reduced, right? But what does it have to do with the reduction potentials, right? Well, the more positive the value of the reduction potential, the greater the tendency for reduction to occur under standard conditions, right? The greater the possibility, right, the tendency for it to occur under standard conditions. So the strongest oxidizers have the most positive reduction potentials, right? Which makes sense because it's such strong oxidizers. What do they like to do? Rip off electrons, right? They like to take electrons. And then the strongest reducers have the most negative reduction potentials, right? The strongest reducers have the most negative reduction potential, right? So here is a nice little chart that's in your notes of the increasing strength of oxidizing agents, right? We start down here with lithium. We go all the way up here to fluorine, right? And then over here, we have fluorine, the ion, going all the way down to lithium metal, right? So again, the more positive the reduction, right? The more positive the sorry, let me say that again. The more positive the value of the reduction potential, the stronger the oxidizing agent, right? The more negative the reduction potential, the more negative the reduction potential, right? The more difficult it is to reduce, right? The more difficult it is to reduce, right? And vice versa, okay? So that's just a chart that kind of demonstrates these key points right here, right? These two things. These are very important points. Strong oxidizers have most positive reduction potential. Strong reducers have the most negative reduction potential, okay? So that brings us to our very first question for today, which is the following is not true about oxidizing reducing agents, right? A, the more positive the value of the reduction potential, the less tendency for reduction under standard conditions. The strongest oxidizers have the most negative. The strongest reducers have the most positive, or none of these are true. The first time I think I put a choice up there that says none of these are true. Okay, so just to go over, the strongest oxidizers have the most negative reduction potentials. Actually, no, that's the opposite. And then the strongest reducers have the most positive reduction potentials. That's actually opposite. And then this one here should be the more tendency for reducing, right? The more the tendency. So the answer there is D. All right, so here's another equation that you need to worry about here, right? Sorry, not worry about, but know. Okay, spontaneous redox reactions produce a positive cell, right? Or EMF, not the electromagnetic frequency that we do to detect ghosts, but the electromotive force. And note that for all redox reactions, this is true, not just voltaic cells, but all redox reactions, this is true, right? And so since there's a Gibbs free energy measure of spontaneity, you can actually there's an equation that actually relates Gibbs free energy, right, delta G, into the reduction potentials, okay? So here is how they relate. Delta G actually equals negative N F E, right? So delta G is the same delta G that we've talked about before, right? The state function from the thermodynamics chapter, right? N here is the number of electrons, okay? And then F here is called Faraday's constant, which Faraday's constant is right there, 96,485. And then E is the reduction potential, right? So just know that a positive EMF, right, or a positive cell potential means what? A negative delta G. Why? Well, if you put a positive cell potential here, right, which means that the E is a positive number, and the negative number in front of the negative sign in front of N multiplied by the positive number of E makes what? A negative number, right? And that's why when you have a positive uh, cell potential, you get a negative delta G, right? What's true then of the opposite? If you have a negative cell potential, then what is delta G? It's positive then, right? So again, that is one of those relationships that you need to know for the last exam, right? And for the final as well. But right now, let's worry about the last exam. Know this equation, right? And I'll probably give it to you on the test, right? But when I ask you a question like, if I have a negative reduction potential, what's my G going to be? Right? Negative or positive. Okay, makes sense? Most of the, it is good stuff. Most of the equations you'll be using, right, won't even be calculations. It will be me asking you about the charges they will be, right? Whether they're going to be spontaneous or non-spontaneous and things like that. So you can actually then relate, right? You can actually then relate the free energy, that gives free energy, right? The oxidation reduction, right? The reduction potentials, right? No, cell potentials, and K. Because remember what K is? K is the equilibrium constant, right? K is the equilibrium constant, right? So here we have delta G, right? Standard delta G, right, or G naught, standard delta G is equal to this, again, the negative NFE, which we saw in the last slide, but then that also equals what? Negative RT ln K, which we talked about back in the thermodynamics chapter. Remember that? Right? We talked about that in the thermodynamics chapter. Okay? So you can actually go back and forth between delta G, the standard reduction potentials, or reduction potentials in general, and K, right? So let's start right here, right? If I have a standard reduction potential, right? If I have a standard reduction potential, I can plug that in there, okay? And then I can plug in the ideal gas constant, the standard temperature, Faraday's constant, the number of electrons that are being moved, right? And then what can I solve for? K, right? Exactly. But then I can do the other way too. If I have a K, right, I can plug in K there. I can plug in Faraday's constant there, the number of electrons being moved, the standard temperature, the ideal gas constant. Now what can I get? The cell potential. Makes sense? Right? Or the standard reduction potential. Makes sense? Right? You can even go this way. You can go reduction potential to standard delta G, which we already did that before, right? If I have an E, if I have the standard reduction potential, right, I can plug it in there. And of course, those are all in the freaking chart that I showed you a few seconds ago, right? And then you put in Faraday's constant, the number of electrons being transferred, right? Solve for that equation, and what do you get? You have a delta G now, right? And then vice versa. If you have a delta G, plug in delta G there, plug in the number of electrons being transferred, Faraday's constant, and what can you get? The standard reduction potential. Make sense? Right? Like all three of these are related to each other, and that's the reason why I wanted to put the thermodynamics chapter with the electrochemistry chapter, right? And keep it away from the acid-base chapter because they are related, but not as well as this. Because now you can also even do this, which we saw in the thermodynamics chapter. Delta G, if I have that, I can plug that in there, ideal gas constant, temperature, and then I can solve for K, right? If I have K, plug in K there, right? Ideal gas constant, standard temperature, what can I get? Standard delta G, or Gibbs free energy, right? You see the relationship there? Know this relationship, okay? Know this relationship, okay? So, let's talk about non-standard conditions then. For non-standard conditions, we have this thing called the Nernst equation, right? And in the Nernst equation, right, let's see how we get there first. How do we get to the Nernst equation? Well, remember this right here, delta G plus delta G standard, delta G equals plus delta G equals standard delta G plus RT ln Q, right? That was an equation that I gave you back in the thermodynamics section. Remember, does anybody remember what Q is? It's a reaction quotient, right? So remember Q and K, they're equal to each other when? Q and K equal to each other when? Yes, they're equal to each other when you're at equilibrium. So what is the difference between Q and K? K is the equilibrium constant, right? Whereas Q is the conditions at any point in the reaction at all, right? So you can figure out what the reaction quotient is at any point in the reaction, okay? But once you get to equilibrium, then Q equals what? K. Does that make sense? Okay, so if you take this delta G right here out and substitute it for negative NFE, which we saw on the last slide, right? And then this one here too, and substitute for NFE, right? Then we get negative NFE equals NFV standard plus RT ln Q, okay? What we can do now is then divide both sides by negative NF, right? Which is divide both sides with the number of electrons in Faraday's constant to the negative. And what we end up with is this. This is called the Nernst equation right here. This is called the Nernst equation, right? At non-standard conditions, right, the cell potential is equal to the standard reduction potential minus RT divided by NF ln Q, okay? So the electrochemists out there, though, they don't like using ln a lot, right? They don't like using ln a lot, so they actually converted it to log, right? They converted it to log by putting in the 2.303 there, right? And when you put in when you multiply 2.03 to the e, well, let me say that one more time. You can convert an ln to a log by including the 2.303, right? And the reason why I wanted to say that again is because I wanted to ask you, right? Because the very first question people ask me is, where does the 2.303 come from? Does anybody know? Anybody know? Where does the 2.303 come from? Why can we use this and put it right here, right, and get log instead of ln? Some of you are in college algebra right now, aren't you? Oh, that's even better. Pre-cal is even better. Pre-cal is actually the class you take after algebra, by the way. That's what I'm saying. Calculus is after algebra. Remember that this is called a natural log. How do you undo a natural log? Oh, say again? No. No. Not the natural log. Yes. Kiara's got it right. It's E, right? To the E, right? So E to the something. And remember that E is equal to what? 2.17. Wait, 2.71? Somebody put E into their calculator. It's either 2.17 or 2.71. I can't remember. Just type in E. There should be an E button on your calculator. Huh? What? It's an error? You should be able to just type in E and get a number. There it goes. So that's what it is. E is 2.718, right? And the reason why you can actually just go from ln to log is because log means log base 10, right? Does that make sense so far? Log means log base 10, right? So you want to somehow get this ln to become a base 10. And how do you make it become a base 10? It turns out all you have to do is do E, right, which is 2.781. Is that what it was? Oh, 2.718, right, to 2.303, and that gives you 10. Do it. After you do that, you can plug in the standard temperature and the ideal gas, right? And then the Faraday's constant, and then what you end up with now is this number here, right? Which will always be the same, 0.0592, right? And now you can solve for either the cell potential at non-standard conditions, right? Or any of the ones that you haven't solved for yet, okay? So I want to do a quick example for you here, okay? I want to do a quick example, okay? Oh, I forgot to change it to, this is the only kind of math that you'll have to do in this chapter, okay? So remember that we had the equation, right? We were talking about zinc, right? Becoming, sorry, I didn't mean to do that arrow. I meant to put plus. Zinc plus copper 2, right? Becomes zinc 2, right? And copper, okay? Remember that? That was the equation that we had. That was the reaction that we had a couple minutes ago on the PowerPoint. Okay. So remember from that PowerPoint of that slide a couple of minutes ago that the standard reduction potential here, right, was what? 110 volts, right? That was that 76 plus what? 34, right? From the chart. Okay. And then how many electrons are being moved from here to here? Huh? How many electrons? 2 electrons are being moved from here to here, right? So what does N equal? N equals 2, right? And then everything else is what? A constant, right? Everything else is a constant. Okay, so quite literally, all you have to do then is say, E, just like in the Nernst equation, equals 1.1. I keep on saying 110. I apologize. It's 1.1 volts, not 110 volts. But 1.1 volts, right? Minus, right? And then this number down here, right? That number right there, because we've already plugged in all the constants. The constant is the standard, the constant are Faraday's constant, the temperature, and the ideal gas law, right? And so that's why we get this number right here, right? And so we put that in there. So that's minus 0.0592, right? And then what goes under the 0.0592? What does it say in the equation? N, right? So the number of electrons that you got, right? The number of electrons, right? So now what do we do with the Q here? What is Q like? Equals what? Q equals what? Q equals K at equilibrium. And so when we do an equilibrium expression, what do we always do? Products over reactants. Remember that? Right? So what is the product over reactants here? The product here is zinc 2, right? And what was the product? Copper 2, right? Don't forget everything you learned before this lecture. So log, right? And then that's going to be then the concentration of zinc 2 over the concentration of what? Copper 2. See? All that stuff there will give you the cell potential, right? So say I gave you concentrations of both zinc and copper, right? And say I said the concentration of copper 2 was, say, 5 molar. And say the concentration of zinc 2 was zinc 2, that's not zinc, there is zinc 2 equaled 0.05 molar. What would I do? I would plug in the copper down here, right? I would plug in the 0.05 up here, right? And then just solve. Yes, because look, right here, log, right? Remember we went through that whole rigmarole trying to figure out how we got from natural log to log, right? With the 2.303, right? So then you just plug those in, right? Yes, that is correct. And so your equation then becomes this. It's going to be E equals 1.1 volts, right? Minus 0.0592 divided by 2, right? Log of what? Exactly. 0.05 over 5, right? And then you just solve, and then you get the standard, then you get the reduction potential at non-standard conditions, right? And then so E then equals should be 1.16 volts, right? So the really cool thing about this is that if you're ever stuck out in the desert, right, and you need to start a car because your battery's dead, right? If you have a copper electrode and you have a copper electrode and you have a zinc electrode and you just happen to have like some zinc chloride with you and some copper chloride with you, literally, right? You can try, like, you can plug in different concentrations, right, of each one, which you should always start out with a very, very large amount of the zinc, right? And sorry, the copper, a very large amount of the copper, and then a very small amount of the zinc, right? Until you get up to 13 volts, right? And then you can start your car. Like literally, that's how you you can do that to figure out how to start your car. It's great stuff, isn't it? No, seriously, like if you had a copper electrode and a zinc electrode, and you had copper chloride and zinc chloride, and you just plugged in like a really big number for the copper, and then a very small number for the zinc, right? Try to make it as big as possible, like as much as you can do, and do it as much as you can until you get up to 13 volts. You can literally hook that up to your car and start your vehicle with it if your battery was dead. Like I'm no joke. The credit doesn't go to me because people have been doing it for a long time, right? Like people figured this out a long time ago. So, but yeah. So the only type of like actual calculation you'll have to do in this particular section right here is with this Nernst equation and figuring out that kind of stuff right there, right? Okay. And then that's probably like the hardest one, the hardest type on the exam. This kind of stuff is real easy. It's like just plug and play, like plug in the numbers and then get the answer, right? But this one here is a little bit more difficult because you have to figure out what the KEQ is, right? The Q is, and then also plug in calculations, concentrations, okay? So that's the hardest thing you'll be doing on this exam as far as math goes for electrochemistry. So that takes us to this question here, which I don't even know if I should let you guys do it since no one's phone works. Huh? I thought there was 3 of you guys that didn't have phone working. I could have sworn I thought it was you, Mary, Naraya, and Oceana wasn't working. Yours is working? Oh, okay. Then it is just 2. Sorry. Okay, so in this question, which of the following is true about redox and free energy, right? Spontaneous redox reactions produce a positive self-potential, right? Or EMF. Gibbs free energy is a measure of spontaneity, so a positive EMF corresponds to a negative delta G, right? Or they're related by this equation here, which hint, they are related by that equation, right? Or all these statements are true. I haven't counted them up yet. You talking about the house cup? Yeah, I haven't counted them up yet. You will find out on final exam day. That's why I'm not going to tell you, because if you know about it already, you might not have motivation to even come to the test. 20. We decided to combine them, right? Then we decided to combine two houses. No, I'm doing this in two. I'm doing this in two classes, right? And it's always been 20 points, and then people that don't get first place will get something lower than that. So since we combined both of the teams to like Slytherin, what was it? Slytherin. Yeah. So Slytherin, Ravenclaw, and then Hufflepuff and Gryffindor. It's just going to be 20 points for the team that wins, and then 10 points for the team that loses. Well, that's very optimistic of you. So, okay, what is the answer here? D. It is indeed D. Good job. Okay, so right here, this is something that's called a concentration cell, right? This is something that's called concentration cell, and this is the basis for how electric eels work, right here, right? If you have a solution, right? If you have a solution of nickel, some kind of nickel salt, like nickel chloride or something, that's why it's green probably, nickel chloride, okay? And you have a very small concentration of nickel chloride over here, and a very large concentration of nickel chloride over here, equilibrium is going to make it so that both concentrations are going to end up being the same. They want to make it the same, right? It's a lot like isotonic, hypotonic, and hypertonic solutions, right? Huh? Oh, salt bridge is literally just like Jello. It connects the solutions to each other. Yeah, because it's got salt in it. Like remember, salt is not just sodium chloride. In chemistry, salt can be any ionic compound, right? And so in an attempt to become the same concentration on both sides of this concentration cell, electrons will flow from the anode side over to the cathode side, right? And while it's doing that, you can actually get a voltage from it, right? You can actually get a voltage from it until it reaches this point where both concentrations are the same, right? So it's kind of a lot like equilibrium. Does that make sense? So say you didn't have any, if you say you didn't have any copper chloride or copper electrodes, but you did have two nickel electrodes and you had some nickel chloride, right? You could do the same thing again, right? And make a huge amount, a very, very little amount of nickel chloride on this side and a large amount of nickel chloride on that side, right? And do the Nernst equation and figure out figure out how much you needed to get a voltage of 12 volts, and then you can start your car. Or actually 13, you need 13 volts to start your car, right? Even though you have I don't know if you knew this, but 12-volt batteries in your car actually are not 12 volts. They're actually 13.9 volts. Right. Almost. That's how you can remember it. Because once your battery falls to about 12 volts, it won't start your car anymore. It's got to be way more than that for it to start your car, right? It's crazy stuff. Crazy stuff. It's kind of like when you buy power tools. I got a bunch of power tools for Christmas. I know I shouldn't know about that, but I got a bunch of power tools from DeWalt. And DeWalt has this thing called a 20 volt max power tools, right? Or batteries, XR batteries. They say it's 20 volts, but that's just the maximum it can be. The actual voltage is 18 volts, right? So oftentimes when you see voltages in media, in commercials, and in stuff that you buy, it's always a different number than it actually is. For batteries, 12-volt batteries are actually almost 14 volts. If you go below 12 volt, get even close to 12 volts, it's going to be very hard to start your car, right? And on the other side of it, it's the 20-volt batteries on DeWalt, right? So you can go both ways. It's crazy stuff, man. Learning new stuff all the time here in chemistry class, right? So notice that the Nernst equation implies that a cell can be created that has the same substance on both electrodes, and that's called the concentration cell, right? So that's this right here. This is the concentration cell. I'm going to ask you a question on the exam. Which type of cell has the same solution on both sides? What is it? The concentration cell, right? Because there's nickel on both sides here, okay? And then for such a cell, the cell potential would be 0, but Q would not be, right? Therefore, as long as the concentrations are different on either side, like almost nothing on one side and really high on the other side, the E will not be 0, right? The E will not be 0 because you're always going to have that voltage flowing until the concentration is the same on both sides. Make sense? Right? Any questions about that? Okay. So let's talk about batteries then. Right? The application of cells. Electrochemistry can be applied as follows as batteries, a portable self-contained electrochemical power source that consists of one or more voltaic cells. Batteries can be primary cells, which cannot recharge when they're dead, right? Or secondaries that can be recharged, right? They can also be used to prevent the corrosion or rust proofing, or they can be used in electrolysis, right? So here's some batteries. You have the lead acid battery. This is the battery that's in your car, right? And this is the one I'm talking about that is labeled as a 12-volt battery, but is actually in actuality what? It's like 14, almost 14 volts, right? There's the alkaline battery, which is the one that you most know, double A's, triple A's, those kind of things. Then there's the nickel cadmium or nickel metal hydride batteries, right? Cadmium's toxic and heavy, so hydride batteries are replacing it. And then the lithium ion batteries, right? The lithium ion batteries are the ones that are in your power tools, they're in your phone, they're in your laptops, right? Those are all the types of batteries you should be familiar with, okay? So here's a lead battery, okay? So and it even looks like a car battery, right? It looks like a car battery. So the electrolyte here, the solution here, right? So in the previous solutions, we had things like nickel chloride, we had, copper chloride, stuff like that. But in a lead battery, right, the cathode is lead, right? Uh, um, is lead based, right? And the liquid, the solution here, has sulfuric acid in it, right? That's the reason why when you have a car battery, you've got to dispose it properly. You can't just throw a car battery in the trash. You have to take it back to Walmart and they dispose of it, right? That's why they give you back $35 when you get it replace your car battery, because they call it the core replacement fee, right? And that's because they're encouraging you to please bring back your dead car battery because it's dangerous and you don't want to just throw it in your trash, right? It's also for environmental reasons, okay? In a alkaline battery, so this is like a shortened version of like, I guess, a double A or a D battery, right? The anode here is zinc plus some calcium, potassium hydroxide. The cathode here is manganese oxide plus graphite. And so, as you already know, right, electrons flow from the bottom to the top, right? Good stuff. Here we have a lithium ion battery, the same kind of battery that's in your phones, your laptops, your power tools, okay? The anode is on this side right here, and the cathode is on this side, and the thing that separates them here, the electrolyte, is the lithium, and that's why they call it lithium ion, right? That's why they call it lithium ion, okay? Current, again, flows from the anode over to the cathode, right? And if you didn't know this, the vast majority of the batteries that are in phones are all around 3.8 volts, right? So oftentimes people will try to buy other phone batteries from eBay or something that are claiming, man, these batteries are way stronger. They have 4 volts. You'll get more runtime on it, right? But no, the vast majority of it's all scam. The vast majority of them are 3.87 volts is actually what it is, right? Or 3.7 volts, somewhere around there, okay? So don't fall for that marketing scam, right? 4 volts just means that, right? The same way 20 volts means 18 volts in power tools, okay? So, next question. Which of the following is an example of a battery? We have the lead acid battery, the nickel cadmium battery, the nickel metal hydride battery, or all these batteries are actually batteries. Since you just got here, Aubrey, you're going to have to be in the second group of people to go do your test, your lab. Did you see the email I sent about having to split everybody up? Yeah. Everybody signed in on this one? So the answer for this one here, right? I don't even want to check to see how many people got it right. But the answer for this one here is that they're all types of batteries. Okay? So we also have this thing called the fuel cell, right? When a fuel is burned, the energy created can be converted into electrical energy. Usually this conversion is only about 40% efficient. That's probably why you don't use fuel cells everywhere, right? And then the direct conversion of chemical energy to electrical energy is expected to be more efficient on the basis for fuel cells. But fuel cells are absolutely not batteries. They're a source of energy that must be continuous. There's a source of energy must be continuously provided. So here's a hydrogen fuel cell, right? And so in a hydrogen fuel cell, right, hydrogen and water come from water, form water, sorry, mistype there, from water. The cells are twice as efficient as combustion, right? But the cells use hydrogen as a gas and then fuel as the hydrogen gas as the fuel, right? Because hydrogen is actually flammable, right? And then oxygen from the air, right? Oxygen from the air. So your next question is this: which of the following is not true about fuel cells? Fuel cells are batteries. In this cell, hydrogen and oxygen come from water. Sorry about that. The cells are twice as efficient as combustion, and then the cells use hydrogen as a fuel and then gas, oxygen from the air. I'm going to go ahead and tell you that the answer to this one here is what? A. Fuel cells are definitely not batteries. Okay. So what happens when corrosion occurs, right? Common name of corrosion is called rusting. It's also known as oxidation, right? So here's a water drop, and it's sitting on top of a piece of iron, right? And iron here, right, is actually getting oxidized. It's getting oxidized to form iron oxide, right? And so when that happens, you get rust, and the rust that you see is that red stuff right there, right? Literally, the rust that you see on things is iron oxide being formed from iron getting oxidized. It's crazy stuff, right? How do we prevent corrosion then? Well, you can prevent corrosion uh, by using zinc because zinc is actually more easily oxidized than iron. So oftentimes what they'll do is they do this thing called the sacrificial anode, and so the thing that gets oxidized first will get rusted, right? And then the thing that you don't want to get rusted, the iron, won't get rusted. So that's called a sacrificial anode. Kind of cool, right? So here's a picture of that, right? So if we have zinc there, okay, zinc here will go through the process instead of the iron will, right? And so the iron will not be oxidized, right? The iron is not oxidized, but the zinc will be oxidized. So oftentimes what happens is that you get iron at the bottom and you get a zinc coating, and then we have a zinc coating, you protect the iron from getting rusted, okay? That happens a lot, of course, in pipes underground, right? You don't have to answer this one. I just want to keep on going because I only have a couple slides left. I want to finish this, okay? So there's also this thing called electrolysis, and that's why I actually have this up here right here, this little beaker and this little 9-volt battery right here, right? Because I wanted to do a quick demonstration for you, right? And in electrolysis, what you can actually do is you can run a voltage, right? Run a current through, of course, we already know, molten sodium chloride, molten sodium chloride. Remember that regular salt by itself can't conduct a current, but when you melt it, it will conduct a current, right? And when you do that, you actually make some chlorine gas from the chloride side, and you make some sodium metal, right, from the sodium side, right? Same thing can happen over here with nickel and steel, okay? So the reason why I wanted to show you this, though, is here I have salt water, right? Here I have salt water, and I have two electrodes connected to a 9-volt battery, right? And when I stick the electrodes into the water, right? The salt water, ouch, ouch, right? What you can see is, do you see bubbles being formed on the left side, the right side? You see the bubbles, right? You see the bubbles? You saw this in my office a second ago. You see the bubbles being formed right there? Yep. You see the bubbles being formed on the right, your right side, right? The right side electrode. Yeah. So I'll tell you what's happening here in just a second. You see the bubbles, right? See the bubbles? Wow. Yeah. So what's actually happening here, right, is that when we do this, this is actually doing an electrolysis where we're splitting the water molecules in half, right? And turning the sodium chloride in the water into sodium hydroxide, the base, right? So the gas that you see that's coming up over here on the cathode side, on your right side, that gas is hydrogen gas being produced. Hydrogen gas, right? Because remember that H2O, right, and sodium chloride, you only need one H and one O to make sodium hydroxide, right? So what happens to the other H? It becomes hydrogen gas, right? And that's what's being produced here in this electrolysis, right? And so interestingly enough, on the other side, right, the anode side, can anyone tell me what's being produced on the anode side? We already have the oxygen being a part of sodium hydroxide being made. We have one hydrogen being made, right, from the sodium hydroxide. The sodium is going to sodium hydroxide. What is left? No, we're talking about this. Chlorine, right? So literally what's being made on the right side, my right, but your left, right, is chlorine gas. Now someone tell me why you can't see the bubbles from the chlorine gas as much as you can see the bubbles from the hydrogen. There's a very chemical and very obvious reason why you cannot see the chlorine gas being made, right? But you can see the hydrogen gas being made. Think about the solution right here, right? What is this a solution of? Yes. What's got more there? What's the solvent and what's the solute? The solvent is the water. The solute is the what? The salt. What's in greater abundance? The water is, right? There's a crap ton more water in here than there is what? Salt. That's why you can only see what? Hydrogen gas being made instead of the chlorine gas on the other side. Does that make sense? Right? Your chemistry is supposed to make sense to you, right? The numbers that you read, the numbers that you get on batteries, everything you do in this class is supposed to make sense in your everyday lives, right? If you have a crap ton of water and just a little bit of salt in here, right? And you're making chlorine gas from it and you're making hydrogen gas from it, right? What's more which one is going to get more made of? The hydrogen gas, because it's mostly what? Water, right? It's mostly water. Now you sit there long enough, you can accumulate some chlorine gas and maybe make like a chlorine bomb and throw it in my office or something and kill me if you wanted to, right? After the tongue lashing I gave you earlier today. But anyway, so this is the last of it, the last of this lecture, the last lecture we're doing in this entire semester, right? It is very sad because I really want you to come away from this class seeing how, seeing the world in a different way where you actually know what's happening in the world, right? So electrolysis is non-spontaneous reactions, right? Non-spontaneous reactions can occur in electrochemistry. How do you do a non-spontaneous reaction? This is a non-spontaneous reaction, right? Turning sodium chloride into sodium hydroxide is a non-spontaneous reaction, right? But we can turn it into a spontaneous reaction by doing what? Adding in some energy, right? Putting in a battery, right? So that's why it says if an outside, right? If an outside, so it's not even spontaneous now. You're just driving the reaction, right? Using outside electricity source. Does that make sense? Right? And then if you use an electrical energy to create chemical reactions, that's called electrolysis, which makes sense because you're breaking the water in half, right? And that's the same thing as doing a lysis, right? And what are you using to do that? Electricity. That's why it's called what? Electrolysis, right? Or electrolysis, to be fast. Then these are all the things that you need to know, right? All the different terms you need to know, right? Which you can just look at that later. I'll give to you on the test, right? You have the Coulomb, which we talked about a second ago. It's in Faraday's constant. Here's Q. There's Q, the charge, the Q of the current. I don't think you really need to know that stuff. I won't ask you about that. You don't need to know about time, but you do need to know the number of electrons, and you do need to know the Faraday's constant. I will give you equations, but I will not give you constants, so you need to memorize those, okay? And there's like 3 constants to memorize. That's it, okay? And that actually ends today's lecture because I just told you all that just a second ago. You don't even have to read that part, right? And we're going to end with this question right here. Answer this last question and we're done for today. And then we can split you guys up for the lab. Well, we already split you guys up. Which of the following is not true about electrolysis? Non-spontaneous reactions can occur in electrochemistry if an outside electric source is used to drive the reaction. I feel like I just did that, right? And then use of electrical energy creates a chemical reaction called electrolysis. And then N equals the number of moles of electrons that can travel through a wire at any given time. Okay? Just so you're not confused too, N can be the number of moles of electrons or just the number of electrons. Okay? Like if you see, for example, on the equation, it's like, a copper 2 becomes a copper, that's 2 electrons. You can use that 2 in the N, right? It doesn't have to be converted to number of moles. Okay? And so, to end this lecture and to end this class, the answer to this question is D, all the above. Okay? So, thank you very much, everybody, for attending class today and attending this class the entire semester. I hope you enjoyed it.